Welcome to Tutorial Haven. Today, we're going to tackle a really core skill for any chemist. And trust me, it's a huge topic for your exams, how to clean up chemical reactions. You can think of it as, well, chemical tidying up. See, when you make a new substance in the lab, it's almost never pure. So the big question is, how do you isolate the one thing you actually want from all the other gunk? Let's dive right in. So, picture this. You've just run your reaction. You're hoping to get one specific pure product, but what you really have is, well, a messy mixture. This is the main problem we're going to solve today. Organic reactions are kind of famous for creating not just the compound you want, but also leftover starting materials, unwanted side products, and of course, the solvent it's all floating around in. We need a way to fish our prize molecule out of that chemical soup. And, this isn't just some abstract classroom concept. Purification is absolutely essential in the real world. Think about it. In the pharmaceutical industry, even a tiny impurity could have really dangerous side effects. Or in food science, it's what keeps our food safe to eat. This whole process of separating and purifying is truly the backbone of modern chemistry. All right, let's kick things off with the basics. These are the first techniques you'd probably reach for, especially when you're trying to separate a solid from a liquid. Let's call this the chemist's fundamental sorting toolkit. First up is filtration. Now, the key word here, the one you've got to remember for your exams, is insoluble. If your solid doesn't dissolve in the liquid, you can just trap it. It's basically a physical barrier. The solid particles are just too big to get through the tiny holes in the filter paper. Simple as that. The whole concept is as easy as making your morning coffee. You pour the mixture through a filter. That solid stuff that gets left behind, in chemistry, we call that the residue. And the clear liquid that passes right through is the filtrate. It's one of the most common and, honestly, straightforward techniques you'll ever use in a lab.
Okay, but what if your solid is dissolved in the liquid? Well, you can't filter it then, can you? That's where evaporation comes to the rescue. With this method, we use heat to turn the liquid solvent into a gas, leaving our dissolved solid behind. This works because the solvent is usually more volatile, which just means it evaporates much more easily than the solid is.
The classic example everyone learns is recovering salt from salt water. You just gently heat the solution in an evaporating dish, the water turns into steam and escapes, and what's left behind? Pure solid salts. This exact same principle is used on a huge scale to concentrate things like fruit juice, or even in forensic labs to recover drug residues from a solution. Now for a really cool technique used to purify a solid that's already solid but just impure. It's called crystallization. And the whole process hinges on one simple fact. Most solids are much more soluble in a hot solvent than they are in a cold one. So we're going to exploit that temperature difference to grow these beautiful, pure crystals. Let's just walk through it together. First, you take your impure solid and you dissolve it in the absolute minimum amount of hot solvent. You want to make a saturated solution. Then you just let it cool down. That's it. As the temperature drops, so does the solubility. Your desired compound can't stay dissolved anymore, and it starts to form this highly ordered pure crystal structure. And the best part? The impurities tend to get left behind, still dissolved in the cold solvent. It's a key step in making pure drugs, like aspirin. Great. We've pretty much got solid-liquid separations down. But what if your beaker has a mixture of two different liquids that are completely mixed together? Okay, let's move on to our next set of tools. This time, we're going to take advantage of a different physical property, boiling point. And that brings us to distillation. The whole idea is to heat a liquid mixture so that the component with the lower boiling point turns into a vapor first. Then you capture that vapor, you cool it back down into a pure liquid, and you collect it somewhere else. So it's heat, evaporate, cool, collect. That's distillation in a nutshell. So here's how the setup works. As you heat the flask, the more volatile liquid, let's say you have chloroform, which boils at 60 degrees Celsius, mixed with aniline, which boils way up at 189 degrees, the chloroform is going to vaporize first. That vapor travels up and into the condenser, which is just a tube with cold water circulating around the outside. This cold surface makes the vapor condense back into a pure liquid, which then drips down to be collected. It's pretty brilliant. Okay, so simple distillation is perfect for separating liquids when there's a huge difference in their boiling points. But here's a classic exam question for you. What do you do if the boiling points are really close together? Say you're separating ethanol, which boils at 78 degrees, from water, which boils at 100 degrees. For that, simple distillation just isn't going to cut it. So, here's the crucial point. For liquids with close boiling points, you need a more powerful technique, and it's called fractional distillation. The key difference, and listen up, this is your exam keyword, is the addition of a special piece of glassware called a fractionating column. This one extra piece makes the separation way, way more efficient. See the apparatus on the left? That's simple distillation. Now look to the right. See that tall, packed column stuck between the flask and the condenser? That is the fractionating column. It's usually filled with glass beads or rings, which gives it a massive surface area. And here's why that matters. It forces the vapor to go through tons of little cycles of condensation and revaporization as it rises. With every single cycle, the vapor gets more and more enriched in the more volatile component. It allows for an incredibly precise separation. This is exactly how crude oil is separated into gasoline and diesel. And now for our final, and maybe the most versatile method of all, chromatography. Honestly, the best way to think about it is like a race. You have a mixture of different substances, and you basically make them all race along a track. And because they all travel at different speeds, they spread out and separate from each other. Okay, so in more technical terms, the separation happens because the components in your mixture spread themselves out differently between two phases. You have the stationary phase, which, like the name says, doesn't move. Think of a strip of paper. And then you have the mobile phase, which does move. That's the solvent that creeps up the paper. Some substances are going to stick more to the paper and move really slowly. Others are going to prefer to dissolve in the solvent and get carried along much, much faster. So what you do is you put a tiny spot of your mixture on a starting line. We call it a baseline. Then you dip the bottom edge of the paper into a solvent. As that solvent, our mobile phase, creeps up the paper, it carries the mixture with it. But since each component races at a different speed, they separate out into a series of distinct spots. It's a fantastic way to separate all the different colored dyes in a black ink pen. Now, not only can we separate the spots, but we can actually identify them using a special calculation. It's called the retardation factor, or just the RF value. The RF value is super simple. It's just the distance the spot moved from the starting line divided by the total distance the solvent moved from that same line. So what's the big deal with this RF number? Why is it so important? Well, because under the exact same conditions, the same paper, the same solvent, the same temperature, a specific compound will always have the same RF value. It's a characteristic property, just like a boiling point is. And this is what transforms chromatography from just a separation tool into a powerful identification tool as well. It's like a chemical fingerprint. Okay, I know that was a ton of information, but you're doing great. To make sure all of this really sticks for your exam, let's lock it all in with a quick fire review. This is the part that will really help you secure those top marks. This table right here, this is your ultimate cheat sheet. It connects every technique to its core principle and tells you exactly when to use it. Got an insoluble solid? Use filtration. Separating two liquids? You check their boiling points and choose distillation. Trying to purify an impure solid? Crystallization is going to be your best friend. Seriously, I recommend pausing here to really let this sink in. This is exam gold. And finally, these are the little details that show an examiner you really get it. If a question mentions distillation, your very first move is to check the boiling points. If they're close, you absolutely must mention the fractionating column. Nail down that RF formula, and know the crucial difference between using the word insoluble for filtration and soluble for crystallization. Believe me, these keywords are what separate a good answer from a truly great one. And that's our grand tour of purification techniques. It might seem like a lot at first, but it all comes down to choosing the right tool for the job based on the physical properties of your mixture. You absolutely have this. Thanks for learning with us here at Tutorial Haven, where we focus on smart exam prep. Keep practicing and you will master this stuff.